on the second day. I see we've got a nice committed audio crew with us. The name of this talk is Android Audio, Everything is Awesome. For those of you who have done audio on Android, you may be looking at me a little weird right now. How can he possibly say everything is awesome? It's a little gag. I am not here to tell you that the world is perfect, or that we are even all that close to that. However, things have gotten a lot better over the last couple of years, and that's going to be the main focus of today, is some of the things you can do to really leverage work that's been done over the last 2 years. Real quick before I get going, how many of you are Android people? Android developers? Looks like I got the gung-ho Android users in here. Great. How many of you have used any of the audio APIs on Android? Media player, audio record, audio track, OpenSLES? Anybody who's dug into that stuff at all? All right, cool. So maybe at the end of the talk, we can talk a little bit of C library, stuff like that, where you can really start to nail low latency audio. So real quick, okay, Google, set a timer for 30 minutes. Well, Google failed me, so we'll just go for it. That's the problems with speech recognition on devices, I guess, right? It's not working all that great sometimes. So who am I real quick? My name's Nathaniel Waggoner. I'm the Android lead for a company called Zap Media in DC. We are functionally an audio company. We extend user interfaces on mobile through voice. What that means is that we serve advertisements that are voice enabled. We also provide a set of other extended functionality through voice, such as showing featured content in applications, pointing users to specific sections of applications, etc. We've launched with NPR One. We've launched with JCAPS and WEEI, who you may know through ESPN. They do a lot of sponsorship with terrestrial radio streamed over applications. And we have some other people in the pipeline. I can't really tell you who they are, but I would keep your eyes open for about 6 months, and you will be seeing a lot more of us. Before that, I worked on a DARPA project called Transapps. It was bringing handheld devices to the military, and then I got my BS and CS from American University. I did a minor in audio technology. I've been passionate about sound for a really long time. Why are we having this talk today? There's a couple of basic reasons. The first is that audio is really fun. We talk all the time, but we listen to music. We communicate with one another. We, drum. We play piano. We do all these different things all through sound. And I challenge people a lot to think, today is a great example, but when you go home tonight, how many people do you touch? How many people do you write notes to? But how many people do you talk to? How many people do you listen to? The next thing is that audio is really complicated. So your perception of my location in this room right now is based off of the reflections that are happening of my voice in the room. So the reflections of my voice off the floor hit your ear a little bit sooner than the ones off that far wall, than the ones off the ceiling, than the ones off the back wall. And that goes a long way into how you determine location in space. There are some really interesting things around that. For example, it's much harder to tell that someone is behind you than it is to tell that they're in front of you in sound. And without some other cues, that becomes very complicated. When you take those reflections out, these things become tough. And then finally, audio is underutilized. I hope Jared kind of convinced you that there is this growing push towards voice that's coming down the pipeline. And we need to keep our eyes on that, and hopefully today we can start to show you some of the things you can do with audio on Android. I've included some typical audio files on here, a random dude with a lot of headphones because I thought he was kind of funny. But then Janelle Monáe, one of my favorite musicians, who has an album called The Arch Android, which is perfect for this talk. And then, of course, Frank Zappa on a tractor. These are all people who care very deeply about sound. And that's what you really need to be if you want to get good quality audio on Android. What are our goals today? Fundamentally, it's to be in the trenches with audio on Android. We're going to talk about audio. We're going to talk about Android's audio architecture. We're going to talk a little bit of Java, a little bit of C, implementation details, some issues you'll run into, and some fixes. And then hopefully at the end, some closing thoughts and some questions if you guys have them. So what is sound? Fundamentally, it's a vibration that propagates through a medium, typically as a wave of pressure and displacement. That's the Wikipedia definition. The really important thing when you think about sound to take away from that is that we represent it as a wave. And the reason that's important is that we take pictures of these waves that we call samples. Samples have a couple of characteristics that we care about. The first one being sample rate. That's how frequently we take these pictures. And then that's measured typically in hertz to kilohertz. There's a really interesting theorem called the Nyquist theorem, which basically states that any frequency that you want to capture, you need to sample the sound source at about twice the rate of the frequency. So if you want to capture a 10 kilohertz tone, you need to sample at about 20 kilohertz. So typically, when you hear 44.1, that's probably a common sample rate. People are familiar with the room, maybe 48K. That's because the range of human hearing is around, I think the low end is like 10 or, yeah, I think it's 10 hertz to about 20K. So we usually add a little bit of buffer on top for the really, really hardcore audiophiles who swear they can hear 25K tones or whatever. We add a little buffer, that's why you get these 44.1s, these 48s, or 96K in the case of the absolute gung-ho, you know, I'm really committed and I have the $350,000 cables that run from my speaker to my digital audio converter. The next thing is bit depth. That's how many bits we use to represent each sample. Typically on Android, we use 16-bit PCM. That stands for pulse code modulation. I won't go into the details of PCM. It's complicated. There's a lot of electronics there, and I don't even pretend to understand all of it. The big thing with bit depth is don't confuse it with bit rate. That's something that has to do with the rate at which you play bits back. And something to think about when you think about bit depth is it represents basically the number of discrete values each sample can take. And so when you hear really crunchy audio, like from an old Nintendo cartridge, 8-bit audio, that's because you can't represent very wide dynamic ranges. And so the sound becomes less and less an accurate representation of the original source. Finally, this is less of sort of a core of samples, but this does really play a big role on audio on Android, is the encoding. Again, we use .pcm most of the time. That's just raw numbers coming off of your device. There's also waves, which are actually typically just PCM audio with some header information, some metadata attached to it. There's .ogs, I won't go into those, .mp3s, compression-based waveforms, et cetera. And then .raw is another way of saying .pcm. There's tons and tons of these. They're very expensive codecs that you can spend a lot of money on to compress and decompress and do all sorts of fancy DRM management on your audio files. We're not going to talk about that. So let's talk a little bit about Android's audio stack. It's a little bit of a weird diagram here. The layers we care about today are the application framework and the JNI layer. We also actually care a little bit about the Linux kernel because in 2013 and 2014, the Android audio team started exposing some APIs that allow us to control the scheduling priority with which our audio threads are executed. And this is a major component of what allows us to start to achieve better latency performance on Android. We don't really have a whole lot of actual control of the kernel, but we can do some things that let us execute at a little bit higher priority. We'll get into that a little bit later. The other big thing here to look at is the hardware, the HAL layer. I'm totally blanking on what that stands for. Thank you, extraction layer, that word abstraction. That's where the vendor bugs start to creep in, and vendor bugs are a major source of problems with Android's audio system. They've actually done so much good work over the last 2 years or so that if we could really nail down the HAL stuff, we would be getting a long way towards being very close to high quality Android audio. So let's talk a little bit about I/O. You saw a demo from Jared where he recorded his voice and got some feedback. That's called input, or the I in I/O. That's really just converting sound waves to bits. We do that with microphones, this guy right here. The fun thing about mics, if I screw the top off of this, I won't do it because the sound guys will kill me. But if I were to do that, you would see there's this little vibrating diaphragm on there, and that's responding to the waves of pressure in the air and is attached to some hardware that converts that into electrical signals. Those electrical signals hit something called a DAC or an ADC, so analog to digital converter, digital to analog converter. And those are the things that actually convert these physical electrical waves into bits and bytes and et cetera. The other part of this in I/O is output. That stands basically is just converting the bits back the other way. So if you've ever looked at a speaker and watched it vibrate, that's the act of creating mechanical pressure waves in the medium of air. It's just vibrating at a specific rate and specific pattern that recreates the original source signal represented by the bits that we earlier converted. A big source of latency on Android is the conversion point, so that's the DSP, or digital signal processing. The two key ones being the DAC, the DAC, and the ADC that I was talking about. Typically, hardware bugs will creep in at that point. Vendor implementations will cause a lot of problems there. So I'm going to show you a little demo. I was going to try and do it through the speaker system, but we ran into some problems. This is a zap, and I want to use it as a use case. So I'll swing around. Oh, yeah, there you go. So this is a podcast I do with a friend of mine.
I'm Matt.
I'm Nathaniel.
And we are so excited about Fallout 4 being announced.
Oh man, I am so hyped for Fallout 4. You have no idea.
It's a pretty. I'm excited too.
No,
Not as excited as you.
I am on the hype train. Woo, woo.
Yeah, are you gonna pre-order it?
I think so, man. I know I'm gonna buy this game. Might as well pre-order it.
Those games are always too buggy for me. I just can't.
That is true. We need to hear what you guys think. So after the beep, just say pre-order
or wait a while.
Pre-order. Live demos are always so terrifying, I guess. So I think a lot of weird things are going on, but the important part of that, ignoring that, is that there were three basic components to that. There was a base audio, a prompt beep, and a listening section. So the reason those things are important is that for a good audio experience, those three things need to be related to each other in time. They need to behave in an expected manner for the user. And we need them to happen in close proximity, right? We need them to be correct all the time, consistent. So we call those the base audio, the prompt beep, the listening period. And there's a few issues with this. The first is that playing sounds with low latency, as I pointed out, is kind of tough. Short sounds, so the prompt beep being the big one here, have a lot of problems on Android. They get cut off, they get distorted. There's inconsistency when you release them in the wild. Our code is now running on many, many thousands of devices, and as any of you who've released a Android app into the wild know, that's just bug reports coming to you all the time, right? Gets much more complicated with audio. In addition, most people who use audio on a regular basis these days are increasingly using Bluetooth extensions, so headphones, speakers, etc. They're in your car, you might attach to your car speaker, that kind of thing. And when you talk about Bluetooth, there's an extra layer of latency because the devices themselves have their own audio buffers in them. That adds unexpected latency that the device doesn't know how to deal with, and that creates callbacks from completion listeners, say, that are delivered early when compared to what the user is experiencing. That buffering is variable by device, so different manufacturers are going to have different levels of buffering, which creates uncertainty again within your application and for the user. And the microphone that is supposed to be doing all this great capture work is actually probably not on that device. Some headphones have microphones on them now, but if they're using, say, a Jawbone speaker or a JBL Bluetooth speaker, that won't have a microphone on it. And so all of those create a lot of uncertainty both in your application and in the user's interaction with it. There are, of course, these other issues I pointed out, the inconsistencies, the vendor-specific bugs, and us being app developers have to deal with a lot of difficulties around weird API issues. So what is the problem? It's latency. I've been talking about it the whole time. It's fundamentally the basic issue that we deal with. And all that means is it's a period of delay between when a signal enters and exits the system. And that can be in either direction. It can be input. It can be output. It isn't really relevant where, what section you're talking about. It's just there. And that's the real issue. Typically, when you start and when you say play, and a sound actually plays, we want that value to be less than 10 milliseconds. That's what iOS has, 8 to 9 milliseconds typically. How bad is it on Android? There's a new SDK called Superpowered that has made a measurement tool for this available to consumers. And as you can see, these are some big name devices. The S2 is a little old. The HTC One is obviously a little bit old at this point. But these latency numbers are terrible, and there's a reason why Android's audio system is not really known for being top quality. These are the kinds of latency people are dealing with. So what causes it? There's a bunch of reasons. Application, so that's your app doing something stupid. There's the total number of buffers in the pipeline. So audio gets buffered. There's a lot of reasons for this. And the more of those that you have and the bigger that they are, the longer it takes to fill them and process them and deal with them, and passing them between application components adds more latency, et cetera. So all of that really adds up to create, there's a talk from 2013 I/O where the framework itself had almost 400 milliseconds of buffer-induced latency in it. That was in whatever the 2012 Android version was, I forget offhand. And then, of course, there's the DSP-based latency that I mentioned earlier, so the ADC and the DAC. There are, of course, many other things that go into this. The completely fair scheduler is the scheduling mechanism for Android. It is not actually all that fair, and when you set your thread at a very, very high priority under CFS, that's guaranteed over the long term, but in the short term, there are no guarantees that you will get scheduled with the priority you set. There's, of course, very high priority threads with Sched FIFO. That means they get pushed to the front of the scheduling line all the time. Those threads in the past would have been pushed in front of your audio thread because it was not running with Sched FIFO. There's something called priority inversion. So that's this idea where your audio processing code is being blocked by a lower priority thread because of something you've said to do. Maybe you're waiting for a UI element to update. That UI element is a lower priority thread. It's being blocked. Now your code is blocked by that thread. There's a lot of other stuff here that I'm not really going to dig too much into, but we can do a lot about those first three now. This man, Glenn Katzen, took over, at least as far as I can tell, in 2013. If you guys want to see where I learned a lot of the stuff that I'm presenting today, there's a lot of great talks from him from 2013 I/O, 2014 I/O, and then some of the I/O Bytes stuff that's going on. He's done a great deal of work providing new APIs to us, new tooling, et cetera, that really help us work through this. Some of these things include decreasing the total number of buffers in the pipeline, increasing the audio thread priority, changing the way audio threads are scheduled, and something called lowering jitter. So when we talk about jitter, what that means is we expect audio callbacks to happen on a very regular basis. We want every 16 milliseconds or so, we expect the audio thread to get processor time. If that callback is late, we refer to that as jitter. That's audible to users as popcorn, basically, which somebody yelled out earlier I thought was very funny. All of those are things that they've been working on since about 4.1. They refer to these changes as the fast mixer, or the fast channel. So how do we do audio on Android? There are two basic ways. There's Java and there's C, and these are some of the core APIs that you'll touch: media player, media recorder, audio track, sound pool, audio record, and then the big guns if you want to drop down to C, OpenSLES, and then this new one I mentioned, superpowered. For those of you who want the TLDR of this talk, if you want the absolute fastest latency that you can get, go to C, use superpowered, because OpenSLES is really freaking complicated. Either way, there are three basic things that you need to do with any audio app. The first is whenever you're going to use a buffer, make sure that you align to the native buffer of the device. So all Android devices have a native audio buffer size and a native audio sample rate. If your source sounds are not running at those sample rates, or if your audio buffers are not the same size, you either have to hit the resampler in the case of sample rates, which is a big performance hit, which basically converts your sample rate into the device's output sample rate, or you get uneven buffer callbacks. So if my buffer is 512, their buffer is 236 for whatever reason, at some point those two buffers are going to fall out of sync, and eventually you'll get an extra callback either early or late to resync those values up. So here's some code for how you do that. In API 17, they introduced this ability to poll the device for that information. So as you can see, there's this API called the Audio Manager, and you just request the sample rate and the frames per buffer. Frames functionally for us is the same as samples. And if that's not the case, you just have to fake it. And you'll note that I put all devices are supposed to support this, and 512 is a nice easy number. 441 is your best bet. There are cases I've seen where that sample rate is not supported, but by and large, going with these two values will give you the best bang for your buck as a developer. So we're going to start with Java, and we'll try and sort of drill down into this a little bit with some code examples. The pros of Java are, of course, that it's pretty simple. You know, we're all used to writing it on Android. It's reasonably effective, so Zap Media right now is using Media Player, which is the highest level API to play most of our audio. I'm in the process of converting us to C, but it takes some time, and there are some serious complexities at scale with doing that. So by and large, if you can get away with it, stick with Java. Again, if you're going to go absolute lowest latency, this isn't the answer for you, but if you're going to do that, you have to make some really serious trade-offs about what devices you're willing to cover and how much time you're willing to put in. Yeah. So I'm doing research into which of those we want to do. The superpowered SDK, the problem with it is it's very new, and there is no community around it at the moment. So if you're at all somebody who's Stack Overflow stuff or wants community support, they don't really have it. They are very responsive, and if you email them, they will get back to you. But it's a new SDK, and bringing new technology into a production pipeline is always a very serious consideration. The problems, again, with operating in Java, though, are it's very slow, and there are some irregularities. If you want to go low latency in Java, use Soundpool. It's currently the only Java API that does output that is on the fast mixer. So what that means is that Soundpool actually gets scheduled with sched FIFO, which means it will always get pushed to the front of the line in terms of processor time. If you can't do that, then you should probably go audio track, except that audio track is kind of a mess, so I wouldn't actually recommend that. And if that's really not cutting it for your latency needs, you have to go C. The biggest issue with Soundpool from a low latency perspective is that it's always loaded into memory. So whatever sound you want to play is going to be fully in memory the whole time you've maintained that Soundpool reference. This obviously doesn't work for very long files. So if you're going to do very large files, again, audio track's probably your better bet. Audio track has a streaming API that you can write audio to and pause and do all those kinds of stuff without maintaining it in memory the whole time. But typically, if you're talking low latency, it's probably because the sounds are fairly short. So let's look at Media Player a little bit more in depth. Pros, very simple. You basically just load a file, you tell the Media Player to prepare that file, and you play. The problems with it, of course, are that it is a giant resource hog, and it is very slow. One tip I can give you about media players is use file descriptors whenever you can. So I've run into a bunch of bugs with Media Player where files will fail to prepare. You'll get weird echoes. You'll get the same file playing twice on top of itself, which sounds a little bit different from an echo. Echo kind of is like da 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 da. This will actually be like hello and how would you like to, sort of offset by a short amount of time. So file descriptors have cured that problem for us in production. I would really recommend you use them. But otherwise, this is it. All you have to do, and then you just press play, Media Player is running. Two key points here. The audio stream. So Android has a ton of different audio streams, notifications, alerts, etc. We're going with stream music because we're presumably playing some music here. And this prepare call is blocking. There is a prepare async version of this, but you have to register a callback. It's a little more complicated, but not too much. And otherwise, it's basically done. The other big thing with Media Player, however, is you always need to release it, and you always need to set it to null. Media player is very large, it's very bloated, it loads the entire audio engine in the C, and if you don't do that, you have a big, very real memory leak hanging out in just waiting to happen, basically. And then here we see the play method. Again, very, very simple. This is just a little method I did, so if it's already playing, we pause it, we seek to the beginning, and we start again. That's the fastest way I've found to rewind and restart a media player from the beginning. And then the big one in terms of completion is that you can set an on-completion listener. You'll get a media player.on-completion listener callback, and you can do whatever behaviors you want at that point. Restart the audio, do some other thing. So in the case of Zap, we play the base audio, our media completion listener fires. We start the prompt audio, our completion listener fires. We start the listening period. Next, we've got Sound Pool, which, as I already mentioned, uses the fast mixer. And the problems with it are, of course, that it loads everything into memory, and it's really only sort of suitable for short sounds. There is a Stack Overflow question here that points out that it's also kind of buggy. I still say Sound Pool is your best bet if you can't use Media Player and you don't want to go C. But do be warned that, you know, the further down into the audio stack you go, the bigger the minefield gets. Wrong thing. So let's take a look at sound pools. So sound pools are a little bit more complicated. The big things you have to do, there are a certain number of streams. So I think the max streams on a sound pool is 16, but I may be making that up. If you look at the docs on this one, it will tell you. Source quality is a totally useless value that gets passed in. Sound pool is capable of playing stereo, so you can dictate whether or not the L or R is louder, etc. 0 is absolutely silent, 1 is normal volume of the sound source. And then you can set a priority. So sound pool priority basically means if you've got one sound pool with multiple resources loaded into it, the highest priority will always take precedence. It can only play so many simultaneously, and if you say play a higher priority sound and you have a lower priority sound running, it will stop that low priority sound, begin to play the higher priority sound. Google typically says in their docs that this API is really targeted at game developers who have lots of like ringing coin sounds or, you know, a duck flapping or a bird hitting a brick or something like that. You can also cause it to loop. I find looping to be really annoying. I typically don't do that, but there are probably cases where people will go, looping, it's exactly what I need. In that case, loop. And then you can change the playback rate. This will effectively give you pitch shifting in a very, very limited context. So you can have the rate at which you play a sound that will correspondingly reduce the perceived frequency of that sound. And the constructors are pretty basic. You'll see this is actually deprecated. There's something called soundpool.builder that they introduced. I'm not using this here because I want this to work back into the past, but that is something that you can rely on. And then you load a sound pool. And what this does is it actually returns an ID from that load callback when the load is completed. And couple of things here. It takes a context, it takes a resource ID, so in this case we're actually loading it from a raw resource, that's why it's a raw ID, and I forget what that one stands for offhand. Priority, there you go. Didn't even use my variable. To play, you just play, these are all the different volume parameters I was talking about, so left volume, right volume, priority, loop, rate, etc. But the big one is the sound ID. You pass that sound ID that you got back from the load into the sound pool when you call play. And that's pretty much it for sound pool. You can stop, you can do all those basic things, and it's still a pretty simple API. That's one of the reasons why I really wanted to point you guys at it. As far as these things go, it's pretty good. Next up, we've got audio track. So this supports static and streaming modes. Static modes functionally is very similar to sound pool. You load it into memory, you play it. It's a little bit more complicated because you actually have to push all of the buffers of content into the audio track. But other than that, it's fairly similar. The big problem here it doesn't use the fast mixer. So if we're going to go through all the effort of using one of these more complex APIs, if it's not on the fast mixer, why bother? But additionally, AudioTrack has a lot more bug issues filed with it, particularly on like Stack Overflow and stuff. People have really run into issues with this API in the wild. But we'll look at it, because that's what we're here to do. Yeah, this is all on GitHub. I've got a Git repo for everything. Yeah, this whole project, everything I'm showing you here today is on Git. I can pull that up so everybody can see the URL when I'm done. I also include makefiles and everything for all the C that I'll show you. So any of that stuff you want to do, feel free. Enter pull requests if you see improvements, etc. So AudioTrack's a lot more complex. That is the big trade-off here as well. We're going with the 512 buffer size, but what I really want to show you is the way we do. Yes, here we go. So this is. Here we go. So when we decide we want to play an audio track, we do two basic things. We play, and then we write. And if you don't write anything to the audio track after you play, it'll just keep polling for audio data. So the big thing here that you'll notice is, in this case, I'm reading from a file. And one of the things that I recommend to people later in the talk is that you don't block in your I/O or in your audio processing threads. And you'll notice that there are probably some issues with that in this code. Don't really look at this for that from a latency perspective. This is just sort of the easiest way to write. I don't remember off the top of my head if this is a blocking call or not, but I think it is. But it's really pretty simple. You take your buffer size, you make a buffer. The audio track actually takes it in bytes, and the PCM audio is 16-bit shorts. So you actually have to double up the size of your buffer and then read the PCM audio in as a byte array. And then we write that out. And then when we're done, we just set play to false, and we call audio track stop. There's also a streaming way to do this, which I think I have in here somewhere. Yeah. Oh, yeah. Okay, so I think we'll have to move on from that one. I thought I had implemented that, but it doesn't look like I've done that yet. So we'll skip out on that one for the moment. And that's basically it in terms of output when you're talking Android APIs. There's some other stuff, but those are the big hitters. Those are the most stable ones, and typically those are the ones you're going to see out in the wild. Then we start to talk about input a little bit. I have till 3 or 3:15. 3? 3? All right. Well, in that case, I mean, we've got... Followed by a break. Well, I don't want to keep people from their breaks. I know during the talks I personally love my coffee. So I can keep rambling. We can do some questions now if you guys want. It's really up to you. Are there any questions at this point? All right, I'll take that as doing a great job. Would you guys like to see some more code? Do you want to? Well, yeah, we'll keep kicking through code. Great. All right. So the next one up is the Media Recorder API. I hate this API. If you're going to record audio, don't use this. Basically, you can do one thing with it, and that's write to a file. I will show that off just so that everybody can see what we're dealing with here, but so basically you set your audio source. In this case, we're talking about a microphone. One footnote: for recording audio, it requires a manifest permission. You don't need a manifest permission to play audio unless you're streaming it from the internet, in which case you need the internet permission, or you're doing something from external storage, for example, and you need to be able to read and write from external storage in that case. You set the output format in this, which we just set to MPEG-4 in this case. And then there's an audio encoder. That's the thing that actually encodes from the audio source. Oh, we'll just get rid of that line. Y'all didn't see that one. Yeah, no, didn't happen. Audio engineers are not known for being very PC, so I'm doing my best. Yeah, exactly. We're very PCM. So the encoder just does the actual encoding. We're just going to use the default one here. And then I have this little file because this project does some other stuff where you can write files to different sources and then pull them into other things. But typically, you're just setting an output file. So this would be a file name. You don't need to do any of this fancy stuff that I'm doing there. And then you call prepare. This is very similar to the media player API. There's a reason for that. These are both part of the same basic audio engine. They use very similar patterns. And then finally, you do this little start call, and it's recording at that point. When you call mediarecorder.stop, it stops, it writes it to the file, and you're done. It's really that simple. There's not a whole lot else here, but again, the only thing you can really do with this is write it to a file. Now, personally, one of the things I really like to do with audio is, say, apply some filtering to it, maybe run an FFT, which gives you frequency content, spectral content for the audio file. You can't do that in real time here. So in that case, you have to move to something called the audio record. Is the text big enough? Okay. Well, you ran into that problem. I went and Googled real quick. So, audio record is substantially more complicated. There's a lot of things you have to keep track of here, and there's a couple of gotchas. The first one is sample rate. Now, the Google Docs are going to tell you that 4400 is the default supported sample rate on all devices. That is true for output. However, for input, this isn't actually true. The only sample rate that I've really found to be consistently supported is 16K. I don't know why that is, but it seems to be functional. I haven't gotten a bug report for sample rate failures since I switched us to 16K. 16K is, by the way, enough to do decent voice recognition. It's what we do all of our voice recognition at Zap in. So typically speaking, this is high enough quality to do any of that kind of work. However, it's definitely noticeably less high fidelity than, say, even 22 or something like that. We do mono inputs because we don't really have a stereo input on Android, so it doesn't really make sense to do much else. And then there's this encoding. We really like to use PCM 16-bit. There are 8-bit and even 32 and 64-bit PCM now supported. They introduced 64-bit floating point audio in, I think, L preview, but we deploy to a lot of people. Not all of them really have that, and floating point, they claim it's as fast and effective as 16-bit, but I'm not sure I buy it yet. And then these two values are really just configuring how big the buffers are going to be. You should try and bring these down, but for ease of demoing, I've kept them fairly high. Here's something that you should really be flagging, though. This is a linked blocking queue. We're going to use it later. This is blocking our audio process when we deal with it. That's something that we want to be aware of. Typically, you would actually use something called a ring buffer here, single read, single write ring buffer, and a set of algorithms called non-blocking algorithms. I didn't really want to dig into that stuff too much, but if you're really, really interested in how to squeeze every last bit of performance, those are some things you can look into. And then we have two threads. We've got a recording thread and a processing thread. The reason for this is that the recording thread needs to not be blocked. If you block the recording thread any more than necessary, you'll lose data, and processing can be very, very expensive. The cost of writing to this linked blocking queue is low enough that you're not going to notice anything, but the cost of, say, writing out to a file or doing any kind of sophisticated signal processing will cause the recording thread to lag behind the actual provision of audio data, and you'll hear artifacting in your resulting source. And then I've got some thread-safe recording detection just so we can make sure we're not crashing or anything like that. And some really excellent returns to generating file names, such as stupid recording is stupid. So what does actual recording look like here? It's actually not that complicated, but there is a little bit some steps to it here. So the first thing is when we call start, you can ignore these lines for now. The important ones are that we start the record recording. That lets the record know to start providing audio data, and then we kick off the recording and processing threads. And we'll find the record thread. What do I call it? go. So all we do is we pull the record into a data buffer. In this case, it's a short array of the size that we declared above, the total number of buffer elements to record per buffer. And then we pass that value in to the actual read method so it knows how much data to provide us. And then we just offer it to that queue for processing when the rest of the system has time to do it. Processing is pretty much the same thing. We pull the buffer for some audio data. We tell it, in this case, to time out after a short period of time, just because it can block indefinitely if you don't do that. And then I have a little thing called my buffer callback that'll handle that audio and do stuff with it. I have two separate cases here. One of them is that it writes to a file. The other is that it actually writes back to an audio track, and I can demo for you guys feedback if you've ever experienced that. As a matter of fact, we'll do that because it's a fun demo. And I think we'll close on that demo. Hello? No, maybe we won't. Hello? Hold on, we're going to restart this guy. This is a fun one. Hello? So, not the best use of your input source, but it does show you that you can read and then write that output fairly effectively. That's a feedback loop, just in case you guys have ever wanted to hear it. It can get much more painful. That's, you know, when you hear like me, if I were to point the microphone at the speaker right now, things would get really nasty. Oh, yeah, there you go. Thank you for that sound guy helping me out. And I think we'll close it on that, guys. Just real quick, in order to stop, you just call record.stop. And again, with all these media APIs, always make sure you release. Always make sure you clear the variable. Otherwise, you're keeping memory for no reason. And thank you very much. If you have any questions, I'll be standing here until break's over. So. GitHub, yeah. 1 sec, I'll pull that up. Android audio examples is the name of the repo. It's got superpowered implemented, and I'm going to start putting OpenSALS implementations in there over the next month or so. I just haven't gotten to it yet. So, any other questions, guys? Cool. Well, thank you.